Hello guys, we will continue our discussion of the dynamics of a particle moving in a straight line in chapter 3. This is point 3.2 that states the following. You can solve problems involving forces by drawing a diagram showing all the relevant forces and resolving in one or more directions as necessary. In this part of chapter 3, we will learn in details how to approach problems involving objects with applied forces and acceleration. So we approach this by drawing a diagram showing the applied forces and acceleration as we showed previously, but this time you will learn how to resolve these forces in one or more directions, then proceed with calculations to find any unknown value. This diagram of applied forces and the represented acceleration of an object is called the free body diagram. So let's go over an example to get into the details of this point. This is example number 4 that states the following. A particle of mass 5 kilograms is pulled along a rough horizontal table by a horizontal force of magnitude 20 newtons against a constant friction force of magnitude 4 newtons. Let's start illustrating this given by sketching the diagram of the object and the applied forces. So this is the particle represented as a box with a mass of 5 kilograms. This particle is present on a horizontal table that is represented by this horizontal line as follows. So this particle is pulled along the horizontal table. And to be pulled, there should be a force pulling the particle as this shown force. The magnitude of this force from the above given is 20 newtons. Moreover, this particle is pulled against a constant friction force of 4 newtons. So the friction force is against the pulling force and the motion of the particle with a constant magnitude of 4 newtons as shown. Then the statement continues as follows. Given that the particle is initially at rest, meaning that the initial velocity before starting pulling is 0, so u initial is 0. This might be used later in this example, so we shall remember it for later use. And this is the given, so let's go and look further at the diagram before going into the parts of this example and check for other available forces to draw. Well, any particle on Earth has a weight which is vertically downwards, perpendicular to the ground, and it is mg. G is the gravitational acceleration. Since the weight is the force of gravitational pull towards the Earth. So mg is 5 kilograms multiplied by 9.8 meters per second squared. Moreover, any particle supported on a surface is subject to a normal force acting upwards, perpendicular to the supporting surface, and is designated by the uppercase letter N as shown. So we are asked in part A to find the acceleration of the particle. So the acceleration is along the horizontal x-axis, and it is directed to the right as shown, since we assume that the box is being pulled to the right. Acceleration is designated by A. So in part A, we apply Newton's second law across the x-axis. This means that the summation of forces along the x-axis is equal to ma. The positive direction is in the same direction as the acceleration, which is to the right as shown. Then let's sum the forces along the x-axis. There is the 20 newtons to the right and positive. The friction force is 4 newtons to the left and negative, so it's minus 4. This is equal to m, that's equal to 5 kilograms multiplied by the unknown a. Then there is the 20 newtons minus friction, 4 newtons, that is 60 newtons, and it's equal to 5a. We divide both sides by 5, then a is equal to 16 divided by 5, that is 3.2 meters per second squared. This is the acceleration calculated in part A. Let's move on to part B. We are asked here to find the distance traveled by the particle in the first 4 seconds. So the period of travel, the time of travel, is 4 seconds. This is the time t, that's equal to 4 seconds. The acceleration that has just been calculated from above, a, is 3.2 meters per second squared. And remember that the initial velocity u is equal to 0, where we remember that the particle was initially at rest as mentioned in the given. So the formula for the travel distance s, as we presented in chapter 2, is as follows. Travel distance s is equal to u multiplied by t, initial velocity, multiplied by time t, plus half multiplied by acceleration a multiplied by the time t squared. U, the initial velocity, is 0 as we mentioned above. So the first term is 0. Then we are left with s, that's equal to half a is 3.2 meters per second squared, multiplied by t squared, that is 4 squared, which is 16. So s is equal to half multiplied by 3.2 multiplied by 16, then the distance s traveled in 4 seconds is 25.6 meters. This means that the particle covered 25.6 meters in the first 4 seconds while being pulled by 20 newtons force along the rough horizontal plane. We move on to part C, where we are asked to find the magnitude of the normal reaction between the particle and the table. We should find the force N, the normal reaction along the y-axis. Then we sum the forces along the y-axis. This sum is equal to MA. We set the positive direction along the y-axis to be upwards, which is along the unknown normal reaction. Then we sum up the forces along the y-axis. There is N upwards and positive, minus W, the weight, which is downwards and negative. That is equal to MA. Since there is no motion and thus no acceleration along the y-axis, then A is equal to 0, and thus is MA. MA is equal to 0. Then N, the normal reaction, minus W is equal to 0. Then N is equal to W after moving minus W into the right side. So N is equal to W, that's equal to 5 multiplied by 9.8, which is equal to 49 newtons. Thus the normal reaction is 49 newtons. This is an example of illustrating the given of a problem of mechanics, where we approach it by drawing the particle or the object. Then we assign all forces acting on this particle, and we draw their force vectors as we did. Then we proceed and apply Newton's second law to find the acceleration of the particle, if we have to find the acceleration of the particle along the direction of this acceleration, applying Newton's second law along the direction of the acceleration. Then we can calculate the distance in a certain time interval while knowing the initial velocity u, and we can calculate unknown forces along any direction if we can arrange a number of equations that's equal to the number of unknowns. In this case, this was the normal reaction force along the y-axis, and we calculated it using one equation and one unknown.